Yeah, good morning everyone. Welcome to Zurich, to Switzerland. For those of you who have traveled far, I know some of you have done that, so I really appreciate that. It's very important to stick our heads together in order to learn from each other how to solve the challenges of the future. I wanted originally to talk on Monday. Unfortunately, I had to be at a very important conference at Bilbao on the Internet of Things. Glad to talk to you today. So the CryptoDatathon. I'll make some suggestions how you can actually contribute to changing the world. Some of you may know that a couple of years back we had big plans with the so-called Future ICT project, and was making a number of proposals like creating a planetary nervous system, a living Earth simulator, and a global participatory platform for real-time feedback, to test mechanisms and to simulate complex systems, and also to do crowdsourcing and enable self-regulation. And these were basically the work packages that we had in mind. So the first three were mentioned already: planetary nervous system, living Earth simulator, global participatory platform, but also social or socio-inspired information communication technology, global systems science, an innovation accelerator, different kinds of exploratories for financial systems, health, epidemics, crime, conflict, risk, resilience, sustainability, energy, and environment. And across all of that was ethics. Now, as you have probably learned, we didn't get the 1 billion euros for this project at that time, even though we were in the final round. But a lot of these things have actually gone forward. So, for example, exploratories have been built, data science has taken off, there's computational social science now, really big, growing quickly. Global system science has taken off. There is this planetary nervous system. Unfortunately, not everyone has access to it. There are living Earth simulator infrastructures. Unfortunately, we don't have access to it. The global participatory platform is still lacking, I would say, so we have to think and work on this. Innovation accelerator also hasn't happened so far, but at least we've made some contributions that you can find at INAC, and I would really encourage you to make your own contributions, because there are so many challenges ahead that we need to be even more creative and innovative, and that can only be achieved by collaboration, I think. Then social-inspired technologies are on their way, and also ethical ICT and design for values. I'll touch upon all of this. The vision was laid out in this collection of concept papers, more than 600 pages, and I'm happy to provide you some copies if you like. And now, here are some of the things that still need to be focused on: privacy, trusted web, and that's one of the reasons, I guess, why you're here. And I'll go through a number of different approaches and how they have evolved over time. So, of course, you know big data analytics. No question, we're living in a time of big data. And in just 1 minute, we're basically sending 700,000 Google queries and 500,000 Facebook posts. And as we go shopping and move around, all of that leaves data traces that basically add up to this big data heap. And then big data analytics is happening. Chris Anderson's dream of that big data analytics was, if we just had enough data, then basically the truth would reveal itself. You wouldn't need theory and science anymore. And also scientists, not anymore. Right? I don't think you probably agree with this, and certainly we've learned a lot in the meantime, and the point of view has changed. But at that time, the idea was you just have to collect as much data as you can. And so people were asking, can we know everything? Can we understand the body, the brain, personality of people? Can we see what is wrong and then basically fix the problem? People have also said data is the new oil. Now it turns out oil needs to be refined in order to be useful for us. And the same thing happens, of course, with data. So raw data in many cases are not very useful. You have to refine them, and this is an art, and we're still learning how to do that. Why? Because the more data you have, the more patterns you will find in the data set, just by chance. So there are a lot of spurious correlations, meaningless patterns that would actually distract you, deceive you, make you take the wrong action if you believe in these spurious correlations. Here's just one of them. Number of serial killers as a function of chocolate consumption. You know, if that would be a causal relationship, it would be very dangerous to live in Switzerland. Obviously, it's not. So this is one of those many spurious correlations. Here's another one. As we're in summer times, you know, number of forest fires correlated with number of ice cream eating children. Strong correlation, obviously, right? Now, if you would forbid those children to eat ice cream or even throw them into prison or lock them up or whatever, you know, that wouldn't reduce the number of forest fires, right? So it can easily draw wrong conclusions. Of course, you would say, oh, that is just a ridiculous example. But unfortunately, it's not. The same kind of mistakes have been made actually by 23andMe. For example, the health authority has forbidden them to sell the product for some time because it was not mature, it was not scientific. If you send a genetic probe to another company, and the third one, they were all making a best effort and had a lot of data, they could still come up with different conclusions about your health and what you might be dying of. And that is a little bit disturbing, right? You would think such a letter should be correct. And so where's the issue? It's sensitivity. Many of the results are sensitive to adding or subtracting a few data points, or to choosing a particular algorithm or another one, or even sometimes choosing this hardware or that hardware, which obviously shouldn't be. But for some time, people haven't paid enough attention to these issues. And you may remember Google Through Trends being one of the examples for big data analytics, big success story in the beginning. And it turns out it doesn't work well anymore, partly, by the way, because they're influencing choice behavior of people in the meantime. But they've taken off this service because you cannot rely on it. And so some of the big success stories of big data analytics have been questioned. So we need something better than that. We need data science, right? And that's why you're here at ETH, right? We want to work with data, but we want to do it the better way. And so this requires basically to combine data with theory. Just take this example over here, epidemic spreading, something that many people are fearful about. Now, if you would visualize who gets the flu or some other disease, and where and at what point in time on a globe, and would see kind of the lights flashing up whenever somebody gets this disease, and would try to find a pattern, you would be going crazy about it because it's not really possible to find a clear pattern. And you can see it in those really broadly scattered data over here. why is this? Well, it's because, do you have any idea? You've done it too. You travel by plane, right? We don't affect each other anymore just on local interactions. We may take a disease to some other country without us even knowing. And so this kind of dynamics, epidemic spreading based on diffusion, as we still had it at times of the Black Death, this kind of dynamics has been replaced by a different kind of dynamics, which is this dynamics. It starts the same way, but then gets very different after a short time. And not only does diseases spread much more quickly in this way, but also in much more unpredictable ways. At least if you don't take into account the travel patterns. Now, if you take this piece of data and define a new distance, an effective distance, then basically you can arrange cities in a different ways, you know, in terms of effective distance from any city that you put into the center. And suppose there is an outbreak of flu in that city in the center, then it turns out in the effective distance there will be a circular spreading pattern. Now, again, it looks like diffusion. So, by combining different kind of data sets and using some theoretical understanding of the process, you can largely improve actually your analysis of the data, and it will come up with much better predictions. This is a way to identify case 0, kind of the first patient 0, the first patient basically who got the flu, which is sometimes difficult, you know, what was the city? And once you have done that, you can also determine what will be the next cities to be hit by the flu and so on. So you can prepare proactively. You can offer a better health service. You can contain the disease much better with limited resources, right? And so here is a comparison of the different representations. So spreading throughout the world and spreading in this effective distance graph, and you can see in the world there's a lot of chaos, but in this effective distance graph there is some clear order. We've also been looking into other kinds of data sets, such as scientific productivity, impact, flow of ideas, global spreading of ideas. So citation data are wonderful data sets, and I'm sure some of you have worked with it. We've also worked on identifying memes, in this case physical concepts, and see how they spread and what were the most important memes. And in fact, it gives a very clear picture of physics as a scientific field and how it evolved over time. You know, I never had such a clear picture before, even though I studied physics. You know, so you find here basically Kondo effect. Who is a physicist here? Yeah, if you see quantum wells, Hubbard model, quantum Hall, Bose-Einstein, neutrino, quark, nanotubes, graphene. Well, a pretty clear picture of what was kind of a big field at what point in time. We've also been looking into the spreading of culture over thousands of years, just using birth and death data of notable individuals. And it's really astonishing how clear the patterns are that you get to see. For example, when America was discovered, people were coming over to the East Coast and then eventually explored the entire country. And many of those artists were ending up on the West Coast because there's such beautiful weather over there, right? You can do the same thing for Europe. You can see how culture basically started in Constantinople, and then Rome became a big center, and then things spread to Paris and London, and from there basically throughout entire Europe. We've been looking into the migration of professionals and into migration of refugees. These are matters that concern us all, in particular also because many scientists are migrants in a sense, right? We're going to other places, and science wouldn't work so well if we wouldn't do such a thing. We have been looking, in this case actually, team of Frank Schweitzer has been looking into spreading of the financial crisis. So this is a visualization of bankruptcies, and you see a clear cascading effect over here. It all started with Lehman Brothers going bankrupt, and then eventually hundreds of banks bankrupted, failed, and that of course created a huge loss of hundreds of billions of dollars. And I wouldn't say the financial crisis is solved. It's just kind of in a sleeping state, in a sense. Then also blackouts in electricity grids have a similar dynamic. So basically in these network systems, sometimes we have a little disruption. And then sometimes you don't even need a disruption, just a little bit of variation. And it might trigger a cascading effect that would have really systemic impact. And that's what we need to understand in order to build systems that wouldn't behave like this, because in most cases that is bad news. If this happens, you're in trouble, right? So we should design systems in different ways, and I won't talk so much about resilience today, but some of my work has been related to exactly this, how to design systems such that they wouldn't show that kind of behavior. Yeah, then also progress in science has been made by crafting new instruments to explore the world, to make things visible that we couldn't see or feel or hear, right? Telescopes, microscopes, and all these kind of things. And so people came up with the idea to create socioscopes. Certainly would like to have new compasses for decision makers so they can take better decisions, and us too, because we're decision makers too in some areas, right? And one of the questions that I was always interested in is social capital, because you can't see it, hear it, feel it, but it's important for the success of a society. Reputation, trust, solidarity, all those things. And we've started to work on this. We never completed this, so if someone of you is interested in working on it and finds results, let's talk to each other, because I think there's potential for a wonderful paper, or even 10 or 20, I don't know. So the idea is to measure social well-being, and indicators could be life satisfaction, trust, cooperation, social network, civic and political engagement, and so on and so on. The kind of data that at that time we've been using is the World Value Survey, the European Social Survey, and Google Trends. And so basically what we've done is we have used semantic differentials or polarity profiles. That means to measure something between two extremes. And this is very important. If you don't have a scale, then basically the results are much less powerful, as we figure out. So basically, you would take opposite words, antonyms, and then say this applies this is more high, this is more low, this is more weak, this is more strong. And anything, any word, any concept could be measured in this way. And then basically you can use different ways of representing the data. So here basically we have been comparing those, the positive and the negative, and weighted them. So W are weights, and the weights had to be figured out by correlation analysis to see which are the antonyms actually that capture, for example, happiness best. So you try to find a way to represent happiness through Google Trends antonyms, and it turns out that with 5 antonyms you can capture it pretty well. Actually 3 or 4 might be enough. So wealth versus poverty is very important. Bright versus dull, famous versus unknown, answer versus question, patient versus doctor. At least this seems to make quite a bit of sense. Now for trust we've done the same thing, and here quite noisy, kind, cruel, the famous, unknown, these are the antonyms that basically capture it. We've done it also with the European Social Survey and for trust and happiness and so on. So this is just a proposal, what you can do with data that are out there on the web, and of course you can do much more than this. You can also try to understand conflict. So one of my postdocs, Thomas Chadifo, at that time had worked on measuring the spreading of international tensions based on analyzing news articles. So it looked for certain words that were representing conflict, were indicators of tension, and counted relative frequencies and so on. And turns out that if you take this into account, besides the classical indicators such as the economic situation, unemployment, and so on, you can actually make much better predictions of war. So basically they're advanced warning signals, which gives you time, like half a year, 3/4 of a year, to engage in diplomacy and economic relief efforts in order to, restore peace, solve the problem. So I think these are really nice applications of data science. And computational social science goes a step further. It combines data science with computer science and social science. And so one of the problems we were interested in is modeling conflict. And one of the conflicts that concerns the entire world is the conflict in the Middle East. So we had the opportunity to look into data where this conflict has occurred. There's quite a lot of data points, unfortunately, as you can see. And we've then done an agent-based simulation and have calibrated that agent-based simulation to the data, and also validated that model, and then looked into different kind of scenarios, such as don't do anything, business as usual, in other words. And this is the amount of conflict that you expect. You could implement a certain kind of political plan. So this was called the Clinton parameters. There was a scenario back to 67 that we looked into, and the Palestinian plan, as far as I recall. So basically you can look into any plan and see how much would that potentially reduce, hopefully, the level of conflict, and where is it likely to happen. It's not that you have absolute certainty about this, of course, but it's still informative about possible impacts. Now, if you want to overcome conflict, then sometimes it's important that people would start to agree on certain things. And even that you should tolerate people being different, you know. Could be an important agreement that can happen many times. So we've made work on social norms because this is about people having different preferences, what they would like to do, but maybe they would end up doing something else because there are incentives for them to adapt their behavior to the behavior of other people, or maybe a new kind of behavior that all groups engage in eventually. So this kind of work is actually telling you how, based on evolutionary game theory, what you can do to change interactions between people such that it would promote social norms or cooperation. And if you do things wrong, then you would have a revolution. So it's really important to know about these kind of things. Or you would have conflict. Of course, you may know me for the work on pedestrians, and that was actually the first subject I've been working on. We were very much interested in understanding phenomena such as this lane formation that you actually observe among people. So after some time, the opposite walking directions are separated. And that happens apparently by self-organization. And there are many other interesting phenomena, such as the occurrence of oscillations at bottlenecks. Let me see whether I can play this video. Yes, it's working. So we can see that there's an oscillation of the flow. We have explained it through the build-up of pressure and the relief of pressure that would actually create such a pattern. It's interesting. It looks like there would be a traffic light or a policeman, but it's not. You know, this happens by itself. That's why we call it self-organization. And that is also my favorite paradigm, really, on how we should go about organizing the world. You know, help it to find its own coordination, cooperation, self-organization. And that requires the right kind of interactions. So it's a mechanism design question. We need to understand how interactions would actually impact the outcome of self-organization in complex systems. There's also stripe formation. That's maybe the most fascinating thing, you know. Just suppose there's a stream of people, say the blue people over here, that you need to cross. And if you were alone, then you know, it would be almost like you're standing in front of a wall of people and very difficult to cross. If there's a stream of other people, however, then what will happen is the stripe formation phenomenon. And you can walk sidewards within the stripe and forward with the stripe because the stripes are moving. And in this way you can cross the stream of people without even stopping, you know. And you don't have to figure it out beforehand. It just happens by self-organization. Isn't that fascinating? So how can we understand these kind of phenomena? We have, for example, developed a social force model for pedestrians. So there's an equation of motion for pedestrian alphas, and then an acceleration equation that's made up, that's the assumption of different kind of forces describing different effects. So for example, the desire to walk with a certain desired speed into a certain desired direction of motion, the actual velocity would be adapted, and that would take some time. Then there are interactions between pedestrian alpha and beta, in many cases repulsive ones to keep some distance from each other, and interactions with walls and streets and so on and so on. So you have a focal pedestrian alpha, and their kind of forces acting on the decision making of that person. With such a model, we could actually simulate all those phenomena. I mean, I showed you the simulation, some of them at least. And so the question is, can you calibrate and validate the models? And at the time when we started with this, we couldn't, because there were no data and it was too difficult to find them. But then eventually, we could do it. So, of course, every one of you could come up with your own model of how pedestrians interact, and then the question is, how good does your model work, right? So this requires data. In just a few possible specifications of the forces, elliptical, for example. And then, yeah, you have to do this validation. How do you do it? Basically, you need trajectory data of pedestrians. So you would go there, take a video camera, which now is very cheap, of course, or several cameras, and extract trajectories of people as they walk along on the plaza or in the street or whatever, and correct it maybe for angle effects and projection effects and so on. But eventually we have trajectories, and that means space-time lines of the motion of those anonymous people. And then you do this. You simulate, based on your model, given certain parameters in the model, you simulate the predicted position of that pedestrian, say, in a second from now, given the motion of the other pedestrians that you know from the trajectories, right? Then compared with the actual position, and so there will be a difference usually, unfortunately, but that's life, you know. And then you want to minimize that difference, and you do that basically for all the pedestrians interacting with everyone else at all the time points in your trajectory data, and then minimize the error, and that gives you the optimal parameter set, right, for each of the models. And then eventually you would see which model is better. We've called that now fitness. That means the smaller the negative number over here, the better. So the elliptical 2 model was the best among all of them over here. And we could confirm the assumption that we had early on, that there was an exponential decay of the strength of the force, the interaction force between pedestrians with distance. And then we looked into angular dependence, and of course people respond much more to what happens in front of them as compared to what happens behind them. And so this is what you can see over here, and that's a simplified model. Eventually, we had so much data we could go towards a data-driven approach, right? So we started doing experiments with Mehdi Moussad and Guy Teroula, as far as I remember. And so students were invited, and they had to do certain kind of tasks, such as walk along the corridor, and you see those table tennis balls. That's not a new fashion, it's just a better way of measuring the motion, so you can really see the details, like the shoulders going up and down with every step, you know, pretty detailed measurement. With 3 cameras, as far as I remember, and you can see the acceleration curve, and it actually fits the model pretty well, so that's nice. And then we have been looking into interactions between pedestrians, and took a lot of students, males, females, different ages, and they all had to do the same tasks, such as passing each other in these experiments. And some of them were taking the left-hand side and others the right-hand side, and we looked into different kind of situations. So sometimes one person was standing, sometimes both people were moving, and so on. And there were also experiments with 3 people, and you can imagine that this is really a big effort, right? This is the way how an experimentalist would go about it. And eventually from the data, you would get a pretty detailed picture of how the interactions happen among people, what's the statistics of it, because it's not a deterministic thing. And we found, for example, that people had a side preference, in this case for the right-hand side, and that the side preference was much more pronounced when both were moving. So there's obviously a mutual adaptation effect which amplifies the asymmetry. So if they both respond to each other, then basically that gets much more pronounced. And that was the force field that we determined from the data. So that was possible. And then we were trying to find mathematical models fitting these data. And so at that time we came to the conclusion that there were basically two fields. One that was determining a reduction of speed when you were basically meeting another pedestrian head on. But if that didn't happen, if we were a little bit to the side, say, then you would change directions and keep your speed more or less, and in this way evade the person. And you overlay that and basically get simulated trajectories, and observation simulation don't match perfectly but pretty well, and in particular for average trajectory. So of course within the range of the standard deviation, and also the asymmetry in the behavior has been well captured. Now that was number one. So validation with experimental data, but then we did another thing. So we simulated a walkway with many people and didn't adjust the parameters to that kind of situation, right? And so the question is, how well would this model be able to predict this setting that it hasn't been calibrated for? And it turns out it worked pretty well, as you can see, particularly the distribution of people over the walkway. You can see the asymmetry because of the preference of the right-hand side. In some countries it's the left-hand side. All is fine with this because right or left-hand side, this is just a social convention that's been formed also based on self-organization. Now eventually these models became so powerful that you could do large-scale simulations of city areas. It's more a hypothetical simulation for the city of Dresden, the center of Dresden. But there are also now applications really for pretty realistic scenarios for urban planning, where you also combine pedestrians with public transport, with cars, and maybe even logistics. And we were interested, of course, in ways to improve pedestrian facilities. And all those pedestrian facilities are made up of corridors, of bottlenecks and intersections. And it turns out you can improve all of those elements. So what architects have done in the past is, in a sense, wrong, can be made much better. So here, of course, the bottleneck situation can be improved by this funnel shape design. Everyone would believe that immediately. But the lesson is less can be more. Taking away space can improve your situation if you do it in a smart way. So we did that here too. So we put some obstacles into the way, and that improved the flow because it helped basically sort out the opposite motion. There was less friction in the flow, so you can see how well this separation works now there's a metro line arriving and people are also walking to the other direction. We'll see after some time those people walking forward are on the right hand side and the other people coming towards us on the left hand side. So the pillars are a very good way basically to help stabilize patterns and separate different flow directions while at the same time being flexible. We've also been thinking about intersection areas. Won't spend so much time on this over here. Now, with evolutionary optimization or genetic algorithm, you can automate actually the improvement of pedestrian facilities. So you would start with an original layout of an architect and then produce copies of this layout, then mutate those copies, apply random variations, and then you would simulate pedestrian flows to test those different layouts and evaluate them according to certain kind of performance criteria. Efficiency is just one of them. And then select the best designs, then again produce copies, modify them randomly, and so on. And let things evolve. And in this way, this bottleneck situation where you have a room and a narrow corridor would eventually turn into this, with some pretty funny intermediate solutions because of the random variation, right? But in the end, what comes out is pretty logical, which is a funnel-shaped solution, a convex one even on top of this. And it can do similar things with other kind of approaches where we have chopped mini obstacles and let them aggregate and interact with the pedestrians, and eventually this evolved into this, a zigzag-shaped solution or an asymmetric funnel-shaped solution. Why? Because when people push, that can create a clogging effect. Stop the flow here at the door, which you don't want to happen. And if you don't want this to happen, you have to take away the pressure on the people standing at the door, and that's why the zigzag shape or this asymmetric solution is absorbing pressure from the people pushing forward. So the people at the door will not be pushed so hard, and they could flow freely through the door, right? And here is a proposal how we could actually improve design elements of football stadiums with this. Yeah. Anyway, I already indicated in the meantime, such kind of models are helpful to get a better idea of pedestrian facilities and how well they're designed. You shouldn't assume that they are 100% accurate, but they would certainly help you identify where would be points that require particular attention, and these are typically crossing flows, merging flows, counterflows. This is what is to be avoided if you have a busy situation. And simulations can help you to get a better idea of what might happen and how alternative designs could improve the situation. I've also been working on modeling freeway traffic, and again, data has changed our picture of what is going on freeways, and by now we have an analytical theory of traffic flow. So there are models, such as the intelligent driver model, IDM, and these models are capable of producing many different traffic patterns for different flow conditions, and these can be compared, of course, with empirical patterns. And if you have a good model, then it would be able to produce all the empirical patterns that are being observed. There would be other models that produce more kinds of patterns, others less kinds of patterns. So basically, data will help you to identify what classes of models are actually suitable to capture what is going on. And so each model class would have a similar phase diagram, as we would say, which shows what are the collective patterns of motion, what are the traffic patterns for a certain kind of flow conditions. The inflow to the freeway, the bottleneck strength, for example, the flow from an on-ramp going to the freeway. And here's a comparison with empirical data, and it shows that the data support actually the phase diagram that I showed you before. In the meantime, we have models that are capable of predicting the extension of congestion patterns and also the delay times. So pretty predictive models. The only thing we cannot always predict is when the traffic breakdown would start, because that depends on overtaking maneuvers of trucks. And that, of course, is decided by the truck drivers. But anyway, we have come up with solutions to improve the interactions among vehicles, so-called adaptive cruise control systems, and we could actually dramatically reduce congestion in computer simulations, at least, even if not all vehicles were equipped with that kind of technologies, say only 10 or 20%, we had a significant improvement of the traffic situation. That is interesting. And so basically, that's the situation of today. Stop and go traffic, everyone is nerved. Simulation is just showing you that we understand the process, that we can simulate it in the computer, and now we'll eventually change the interactions among cars to change the traffic pattern that results from self-organization. Right? This visualization has been done by Martin Schreiber in Dresden, one of my previous postdocs. And so you can see here's an on-ramp. Cars are trying to sneak in the freeway. That produces a small disruption. Those disruptions are being amplified, and that causes the stop-and-go traffic. Now we'll turn on the so-called traffic assistance systems. A certain percentage of cars is equipped with radar sensors that measure distances and relative velocities. And then we let the cars drive automatically, accelerate, decelerate in a slightly different way. And in such a way that we would actually improve the stability of the traffic flow and increase the capacity slightly such that we can dissolve the traffic jam, based on a decentralized approach. No traffic center involved here, just changing the interactions between the cars. So that means we reach the success by real-time feedback, which changes the interactions locally a little bit to create the desired outcome by self-organization. And a similar approach has been taken for urban traffic flow, where we sometimes have this kind of situation, right? And on the other hand, self-organization can sometimes work astonishingly well, right? This is a pretty diverse traffic flow, I would say. And there are no traffic lights, no policemen, and people rarely have to stop over here. And it's the particular design that allows for this. So we have a unidirectional flow in the front. We have the opposite unidirectional flow in the back, and there's a small buffer in the middle that allows people to adjust their speed such they would find a gap in the flow just when they want to cross. That's the success principle. So it's just a matter of design. So, and we said, okay, can't we use self-organization to reorganize cities and come up with a more efficient flow? And we were inspired by the oscillatory flows of pedestrians at bottlenecks and said, interactions are bottlenecks too, so can't we learn from this, basically? And can't we build traffic light control using the pressure principle that would actually produce these oscillations? So the idea was the traffic flows should control the traffic lights bottom up. rather than the traffic lights would impose a certain traffic pattern top-down as we have it today. And what will be better? That's the question. Of course, you would think it's a traffic center that wins the competition. But then it turns out actually traffic light optimization is an NP-hard problem. There are too many parameters that you can vary at every single intersections, and then you can have all the combinations of all the possible parameters of all the intersections. It's just too much even for a supercomputer to solve it in real time. And so they simplify things. They come up with an optimal plan for an average traffic situation on Monday morning, and then they vary a little bit the green times. But they don't always come up with a new cycle, right? There's a periodic scheme altogether. And it sounds like a plausible solution, but you throw away all the aperiodic solutions. And these are the good ones. So I'll accelerate a little bit. This is what you get for top-down regulation as capacity utilization increases. A pretty plausible picture. If you have intersections locally minimize travel times of arriving cars in the incoming road sections, then you find this. So for low capacity utilization, much less queue lengths, but then eventually it explodes. So the traffic control center would say, ha 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 ha, this is actually why you're paying millions to us, that's why you need us, just give us more millions and we'll solve the problem over here. But then there is, so Adam Smith's invisible hand works over here, but it doesn't work over there. And the question is, what happens if you add something which is love your neighbor, coordinate with your neighbor, and based on short-term anticipation, and this produces a better solution all the way. Again, based on decentralized principles, local interactions between cars and the traffic lights and between neighboring traffic lights, that's all. And so self-organization produces coordination. The coordination spreads in the city, throughout the city. And the question is how good will it be if you have not just one intersection, but you have many. And we have looked into this, for example, for the city of Dresden. You see it's a pretty messy setup, terrible. and overall, worst comes to worst, there are a lot of trams and bus lines that cut through this in different ways. And so you want to have a green wave for the vehicles, but you want to prioritize public transport too. And if you prioritize public transport, you would destroy the green waves and it would create a monster traffic jam within just a few minutes. And that's the problem that they had. That's why they couldn't prioritize public transport. Of course, they had a competition for the best system, and they bought the best system, paid a few millions, it's all adaptive. It all produces green waves and so on, state of the art, And then comes Professor Helbing's team and says, forget about it, we'll do it completely different, let the traffic flows control the traffic lights. And so that approach also produces green waves. That's the green waves by the state of the art control. This is our green waves. And see, it looks different. And it looks different because we use the gaps occurring in the traffic flow as opportunities. We're not imposing anything here. We're responding to the traffic flow. And see what comes out. This decentralized, again, a smart centralized control. Public transport gains dramatically, much less delays, but not at the cost of motorized individual traffic. pedestrian cyclists also have large gains, and it's good for the environment too. So this is what you can do if you combine data with science, computational social science. And then, of course, the question is, if you can fix problems locally in cities, can you go global? That is what global system science is about. And in principle, we know, at least since Elinor Ostrom's Nobel Prize, that self-governance can be efficient if you have the right kind of design principles, right? How can we support the self-governance? Basically through digital assistants that can help us to have more situational awareness, to engage in more successful, maybe profitable interactions, will warn us of lossful interaction and painful experiences, will help us to arrange transfers and collaboration and all these kind of things. So, for example, we could try to map resources and who uses them all together, in a crowd-sourced way. And we've started working on this with very little resources. What came out was Swarm Pulse. I'm not sure it's currently operational. But anyway, I think it was a nice project. And we've also been asking ourselves, where can we take quantified self-movement? Can we help people to inform themselves better about their own health? Give them feedback while not losing control of their data and privacy, and help each other to know more about health threats. And GripInNet, InfluenzaNet was one of the projects that we're working on, so people would anonymously report if they don't feel well, if they have the flu. We don't want to know who they are, but we want to know how many people are ill in a certain neighborhood. So people would get this feedback, they would see a map and could decide, maybe I should get a flu shot because I could catch the flu, right? So this is a way of empowering people with information. And yeah, here's just another map that you can see, and we do the same thing with consumption. And in principle, you could even go further and say, oh, we all could actually map the globe in a crowdsourced way. And in fact, a colleague of mine, Mark Polyface, is working on such kind of projects where you can construct a city or reconstruct in 3D based on photographs that people have taken. In terms of crowd safety, other colleagues of mine we've interacted with have created an app that actually provides location data that will then be aggregated, evaluated according to certain kind of quantities, and those aggregated data would then be available to the organizers of the event to help them avoid critical situations. So yeah, you could see these density patterns, for example, and you would basically get a warning by your smartphone if you were to run into a crowded situation, and will help you find alternative routes in order to improve the safety of the event, of yourself, and also the experience that you want to keep. So you can see some of the places get pretty crowded, and then maybe you want to avoid being in that place. I think I'm accelerating a little bit. So basically, the idea is that now the guy or girl gets a feedback on the smartphone and says, there is congestion, warning, you know, better take this other subway station or so. Then, of course, you can create digital assistants for smart disaster response, right? So smartphones can do a lot of things for us. They can also be turned into survival kits for cases of earthquakes and other kinds of disasters. They can be even used to detect disasters, warn your friends, help yourself organize with your friends and neighbors in order to get through that situation, collect information, give feedback, create an ad hoc network so communication would stay alive, have a decentralized payment system, and create a sharing economy that would still run when every centralized infrastructure is broken down. You know, we'd like to be able to help ourselves and to help each other in these kind of situations. You know, it takes 72 hours for the government to help us. So, you know, what are you doing in these 3 days? We should have these tools. And then, of course, blockchain is very important for such kind of applications, not only in the domain of payment. Decentralized systems are known for a long time, so you know the BitTorrents, Pirate Bay, and so on. These were not the platforms, however, to create trusted interactions, right? Obviously, and blockchain makes a difference here. It's not the solution for everything, perhaps, and it also depends very much on the kind of blockchain and how you're using it. So this is a contribution that I've written with some colleagues about the ethical issues and societal issues to consider when you're working with blockchain. And there's so many different areas where you can apply finance, production, logistics, energy, smarter cities, and so on, even fix the internet. And one of the most important areas, I think, is to boost sustainability. We need a better financial system, a multidimensional financial system, a real-time feedback and incentive and coordination system. Because today we're throwing away too many valuable resources, 50 tons a person basically. And how to change that? Well, we could, with platforms such as NervousNet and others, map noise and CO2 and other kind of externalities. That means the impact that our behavior has on the environment and on other people, right? And then what we'd like to do is increase positive externalities, positive effects, reduce negative ones, and ensure fair compensation. And for each of those different things, noise, CO2, aluminium, glass, steel, and so on, you know, these valuable materials would be different incentives, different currencies, different feedbacks. A multidimensional system could be built, of course, with blockchain technology. So our proposal is to bring together blockchain and the Internet of Things, which is needed to do the measurements, right? And in this way, create new forces in our economy, in our society, that would encourage the reuse of resources and thereby create eventually a circular economy and a sharing economy, because that is incentivized in suitable ways, right? And that can be basically organized with decentralized autonomous organizations, and there are actually many decentralized mechanisms to promote cooperation in tragedies of the commons, and also relevant to climate change and overfishing and so on. So we have learned in evolutionary game theory that there are mechanisms that would be game changers, that would change the outcome through self-organization. Among them, repeated interaction, called direct reciprocity, peer punishment, can be effective, but also there are better mechanisms. So punishment is not the best deal. Competition can help a lot. Altruistic signaling is astonishingly powerful. Also, success-driven migration is very powerful, and grouping cooperative people among each other increases cooperation altogether and encourage other people to cooperate. Reputation systems, qualification systems, all of this, and coming back to these competitions, and one of the ways really to unleash the power of the people to the better of our future would be through the Olympics, where we would all engage into finding new solutions to the problems that we have: climate change, energy efficiency, resilience, sustainability, peace, you know. And a lot of inventions can still be made. Those inventions should be public, could be a public good, Creative Commons, open source, and in this way every city could take it and develop it further, and we would learn from each other and help each other. That's the idea, basically. And we would need to have platforms that support it. Our team is working on such platforms too: Empower Polis and Digital Agora. And so if you want to read a little bit more about what we're doing, then these are 2 books. So thanks again for coming here to ETH Zurich. I'm excited, and I hope that you will have an exciting week and exciting projects and exciting collaborations. I'm very much looking forward to seeing what will be the outcome of this crypto hackathon and also of your future careers and collaborations. So let's stay in touch. All the best.
Let's get a few questions, and we have coffee to continue questions. Yeah. Okay.
Yes.
So you mentioned about the pedestrian modeling and the pedestrian behavior analysis. So are you using this technology in terms of the self-driving cars?
Yes, we have been using that as an inspiration of our traffic light control. The self-driving cars, the adaptive cruise control system, is based on variation of this intelligent driver model that is pretty detailed, and so we have changed here parameters in that model adaptively to the traffic situation that's being figured out not only by your car but also by cars in your neighborhood. Would be car-to-car communication to get a better picture of the traffic situation altogether. So the car would respond to that kind of input and change parameters such as time gaps, acceleration, deceleration, such that safety is increased, such that stability of traffic flow is increased, and capacity is likely increased at bottlenecks. Yes?
Is reinforcement learning a good option for controlling this complex system? Could be a good option?
Well, it's certainly one of the tools that are natural to use in this context. Now, the question is control always the right kind of paradigm, right? Control implies that the system wouldn't change. When you apply it to society altogether, it might not be a good thing. Why? Because the environment is changing, demography is changing, resource situations are changing, the world economy is changing, you know? And so a system based on control might be not adaptive enough to those changes. And it wouldn't potentially give enough freedoms for creativity and innovation. We need to be clear that innovation questions existing solutions and systems, right? So if you think we need innovation, then you need to have an organization of our society that allows for those changes to happen, right? So that's kind of the tricky thing, and a lot of the debate that I'm engaged in, kind of on a public and also perhaps slightly political level, is exactly about this. if we control people too much through big nudging and citizen scores, predictive policing and so on, would we have the degrees of freedom that would allow those systemic changes to the better to happen, right?
We have seen a few examples of where big data actually makes sense or is a positive example, and then we have seen examples where rather small data makes sense. So my question is a bit about the usefulness of big data and where are the limits, right? Is it about too many variables? And yes, if yes, what does it mean for participants in the CryptoDatathon? I guess there are lots of parameters that are defining crypto movements as well. So where do you see the limit?
Well, too much data can be a problem too. We know the phenomenon of overfitting, for example. And those spurious correlations are in many cases overfitting problems, right? So it requires some science, I believe, to identify those parameters that are significant for a particular kind of problem, and then to focus on them, how to measure them well, and how to interpret the data well, in order to come up with a good mechanism of organization or even self-organization in the system through real-time feedback. So I think we've learned that the brute force way would not always deliver the best solutions. In many cases it would not. It might be kind of the quickest way of doing things. The brute force way would always give you some advice, but maybe it could be bad advice, you know, misleading. So from that point of view, I think one of the lessons that we need to learn is you can't always trust the outcome of big data analytics or even of an AI system, no matter how powerful it is. AI systems also can be manipulated, can be wrong sometimes, and sometimes it depends really on small details. Like, you know, I could probably show you systems where changing a single data point would change the outcome completely, the advice that you would get, the action that you would take, because of this sensitivity issue, right? So powerful systems are sometimes pretty irresilient. That's the point. I personally believe we are now in a transition phase of our society around the globe because of the digitization, but also because of lack of sustainability. So systems will change, are changing already. But I think in these times, what we need more than ever is resilient systems. And resilience implies the need for diversity and for decentralization, at least sufficient degree of decentralization, which means that we shouldn't be all doing the same thing, you know, have different people make different experiments and then learn from each other and help each other to improve. That's, I think, the right approach. Yes?
Okay. One more question and then we have to continue our coffee. Okay?
Last question.
Yeah.
So talking about solving the existing problems in the society, either top down or down up, have you applied your method to solve the problems for example, for ambulance or for firefighter vehicles? Because for normal traffic or normal vehicles, we are either late for schools or late for work. But if for ambulance, they are late for life and they might lose life. So have you applied any of these analytics to this series?
Okay, so I talked about the traffic light control approach, right? Which responds to the traffic flow. Now what you can do is you can give certain vehicles a higher weight. For example, a bus, we would give a weight of 30, for example, as compared to a car which would have a weight of 1. Of course, you can change that. You could give an ambulance a weight of 100 or even 1,000, and then basically it has a lot of impact on the green wave that will be created. You know, that would prioritize this ambulance car based on principles of self-organization. So that is easy to do.
Okay, great. Thank you.
Okay, let's continue over a coffee, please. We have half an hour left.
Okay.